I also try to visualize some of the interaction between different forces. So when talking about nucleosynthesis, I would say all the forces interact with each other. And at first, you can imagine that if two atoms, when you want to convert, for example, put two atoms together and make them into a new nucleus, of course they need to get in touch with each other first. However, you can imagine that at the beginning, this is a neutron-rich, proton-rich, and this is also proton-rich. So there will be repulsive electrostatic force that will keep the nuclei apart under Earth conditions. And it puts them really, really hard so that they are close enough. For example, 10 to the minus 15 meter. Then the strong force will suddenly kicks in and then sticks them together. But this will be a spontaneous reaction, 就是自发性的反应 spontaneous reaction, only with one very important proviso, 前提, which is, all you know, from Einstein, E is equal to mc squared. Energy is equal to mass times light speed squared. So, if there's a loss of mass, energy will be released so that the reaction will be spontaneous. But if there's a gain in mass, energy needs to be added. So this will not be spontaneous. So that will be sort of like the guideline for the atoms when they want to produce a new atom or new element. So then you already know about this. I will skip this. Isotopes, yes. Isobar, yes. Beta decay, electron capture. Okay. Beta decay, electron capture, and alpha decay. But here I will use the time to give you a preliminary understanding of some important dating methods. The first one is radiocarbon, which will undergo beta decay from C14 to nitrogen 14, which is the most common nitrogen on Earth, you know. And then the next question is, how is C14 produced? The other way around. So from here to here, that will be an electron capture process. Then electron capture, this is used for all carbon-containing material, like your hair, paper, they can be all used for dating. And electron capture, a typical example is potassium argon dating. Where do you use it? Volcanic material. So in volcanic material, there's a lot of potassium. And once it's decayed or it's converted to argon, you can use this process for dating. So like for example, in Taida or Tsinghua, they use a lot of this kind of technique to date volcanic material. The last one is probably also very famous one for some of the students, is uranium thorium dating. From here, uranium to thorium. And it's commonly used in many marine material like suspended particles, sediments, and so on and so on, and corals. So it's a very useful method. And actually, even spontaneous fission can be used for dating. Huh? Really? Yes. There's another method that uses spontaneous fission for dating, but we'll skip it. Okay. Then there's an observation. Elements with even numbers of protons have more stable isotopes than those with odd numbers of protons. So you will see this is even, odd, even, odd, even, odd. Then there was a question, why? To be honest, I myself, I don't know. I would say that would be something related to the stability of the nuclei. That's my guess. So, nucleosynthesis can be divided into 3 stages. So Ethan briefly talked about this. The first stage is right after the Big Bang. The second stage is in the stars. The last stage is under very special events. Then there will be neutron capture. So these are 3 stages. I think today we will only stop here. We can first talk about the Big Bang. It's not much. So this is also called the primordial nucleosynthesis. Primordial means 初始的，一开始。So, it's based on the knowledge of distribution of stable isotopes. Its original matter is neutron, 中子. Okay. And the beta decay of free neutron is only 10 minutes. 自由中子, when it's not in a nucleus, it will decay very quickly to a proton. So, only in 10 minutes. So, at that time, right after the Big Bang, based on some computer modeling, there will be only hydrogen 1, 70%, deuterium, which is hydrogen 2, helium, and helium 4. And there will be also some trace amount of lithium, barium, boron. And these are actually important material, but you can imagine that these are all very rare on Earth. This is so rare that it's actually a hydrothermal indicator. So I myself, I study hydrothermal lesion in the ocean, and we all know very well that helium is the most important parameter for you to quantify the effect of hydrothermal impact. And helium-4, as some of you know, is the most important carrier gas for modern instruments. If you use like a gas spectrometer or many other instruments, you need helium because it's an inert gas. Inert. 惰性的, okay. Inert gas. And it is so rare that I still remember when I was doing my PhD in Germany. And at some point, our technician told us, oh, all of you have to stop your experiments. Then we asked why. Then he said, oh, because Russia, 俄国人, they're cutting their supply of helium. So we run out of helium and all the instruments need to shut down. So you see, it's actually a big problem for future chemists. So it's not renewable. 你没有办法再新增的. Okay. It's not renewable. So once we run out of helium, we'll see. We probably need to use other gas. And these are the elements that is believed to be produced during primordial nucleosynthesis. So you see, these are really rare. So only up to boron. And you might ask, oh wow, there's no isobar 5. It's only 1, 2, 3, 4, 6, 7, blah, 8. So 5 and 8 are missing. And this is because they are all radioactive. So you don't see them anymore. And their lifetime are too short for them to survive, to serve as the parent nuclide for new elements. So you don't see them. So that's all for primordial nucleosynthesis after Big Bang. So the key point today is in stars. But we need to go to the HR diagram, which you already heard about it, but I will talk about it further. Okay, and you know it's proposed by two scientists, H and R, and skip this one. This will be the original version without size information. Okay, so apparently the size is an interpretation, 是一种解释. The original version is like just dots. Okay. Then you will ask, why do we know the size? I'll tell you later. But let's talk more about the two parameters. The first one is luminosity, 光度. It's the intensity of starlight. It's a proxy for a celestial 天体的 object's intrinsic brightness, 内在的亮度 or inner temperature. You can say that. And it's defined as but here there's a definition for when you use luminosity on this graph. So it's defined as the intensity that can be measured at 32.6 light years, which means you need to normalize. 就是把大家都校正到同一个距离 because away from the observers. So there's a normalization involved. And the sun is used as the reference and the value is set to 1. So do I have a colorful version? Where's the sun? 1. Here. Our sun is here. And its luminosity. Here, the unit is solar unit. So you see, everybody is normalized to the sun. Okay, that's about the luminosity. And spectral type is the composition of the starlight. And it's a proxy. Proxy means approximation, 就是一个代理指标，不是真正的测量。It's a proxy for a celestial object's surface temperature. And it's a classification of stars based on their spectral characteristics. So these are the spectral types. So O, B, A, F, G, K, M with different colors. And there's a saying, oh, be a fine girl, kiss me. Oh, be a fine girl, kiss me. Okay. And in fact, they are related to the thing you learned last week. Each spectral type is associated with a kind of dark bands composition. That's why the spectral type is a proxy of chemical composition. But because as you learned from last week, these bands reflect the chemical composition of a star's atmosphere. So, and the relative abundance of ions, you see, some are darker, some are lighter, varies with temperature. So it's a proxy for surface temperature of stars. Then, you may ask, now we know luminosity and temperature, why do we know the size? The answer is because of this equation. Stefan Boltzmann law. Luminosity of a star is equal to 4 pi r squared. R is radius of the star, sigma Stefan Boltzmann constant, and T to the 4, surface temperature of the star. Okay, so now you can think. For a star of the same T, bigger stars will be, question. For a star of the same L, bigger star will be, I let you think about it for 30 seconds. The first question is the cent T. The second question is the cent L. Jackie, can you tell me the answer of the first question? Cent T, bigger star will be right. Bigger star will have higher luminosity, right? Like this. Bigger star have higher luminosity. Andy, second question. Cent L, bigger star will be bigger star will have lower temperature. That will be this. Right? Bigger star, lower temperature at the same luminosity. That's the reason why you see the size interpretation on the HR diagram. It's based on this relationship. Okay, size. So you see this interpretation, right? Correspond to that. Although the original version would be no size interpretation, like this. Okay, summary. As already summarized by first. Here, right? Yeah. Okay. So these are all summarized. Okay. Our sun is not big. Okay. In the main sequence star, red giant and white dwarf. Okay. And so before the HR diagram, we were talking about element formation stars. Key concepts. Stars form by contraction of massive clouds of gas driven by gravity. So all stars are gases. And as the cloud contracts, all its energy is confined to a smaller volume and it heats up. This is because the potential energy, 位能, is converted to heat. So it's like a water coming from high to low, then you will create energy. And it keeps contracting and heating up. So it first contracts, the potential energy is converted to heat, so it heats up until some force operates to offset the gravitational contraction, which is called the radiation pressure, which is the pressure that's generated by heat. And then this heat, actually, because the temperature goes up, it will induce nuclear fusion. At the end, the star is the product of hydrostatic equilibrium when gravity is balanced by radiation pressure. So to visualize, at the beginning, we have two atoms. So this is hydrogen. The mass is 2.0141. And now, the gas is contracting. So the two atoms are closer to each other, and at some point, when they are close enough, the strong force kicks in, and then helium forms. And helium has a mass of only 4.0026. It's lower than the mass of 2 times 2 hydrogen atom. So there's a loss of mass. So yes, check. This can happen. And when this happens, because there's a loss of mass based on the E is equal to mc squared, there will be energy released. And this energy release creates radiation pressure together with heat, so that a star is actually a dynamic equilibrium. Dynamic equilibrium, 动态平衡 between pressure and gravity. Gravity makes the substance contract, and pressure counterbalance the gravity. Then you see a star. And more about energy consideration. So, if now you want to create larger elements, then because in larger elements they are more portable, so the electrostatic force is stronger, the repulsive force is stronger. So, you need higher ignition temperature, 点火温度, to synthesize heavier elements than this. And because you need higher temperature, you need more potential energy, 位能, for stellar dust to reach higher ignition temperature. Therefore, you need larger stars. That's the reason why you need larger stars, because you need higher temperature. Okay. So, this is a table from the textbook. This gives you a brief feeling what kind of star produce what kind of elements. For helium, it can be produced in stars as small as 0.1 of the size of the sun. But for carbon and oxygen, you need double sun. For neon and magnesium 4 sun. Silica 8, iron 15. And that's the ignition temperature in million K. So let's give you an understanding of what can be done for different stars. This is also in the textbook. For a small star, it's basically doing hydrogen burning to helium. For 2 solar mass, it's already red giant. It has a onion structure. 分层的, okay. And for a very big star, like a giant or supergiant stage, it has many shells. Silica, oxygen, blah, 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 to hydrogen. Okay. These graphs tell you why stellar synthesis stops at iron 15-6. This is the end of nuclear fusion in stars. Because based on atomic physics, this is the mass number. This is the binding energy per nucleon. Apparently, iron 56 is the most stable nucleus in the universe. And if you want to fuse heavier elements by nuclear fusion, then you will reach a problem. That problem is there's no mass loss during nuclear fusion. So, in this direction, there's no spontaneous nuclear fusion. You need to add energy. Therefore, the mass of nuclei heavier than iron proves to be slightly larger than the mass of the nuclei that are merged from them. So, which means no mass loss. So, it will stop here. Okay. Now we go back to HR diagram. So now we will talk about the life history of different stars, of different sizes. So, most stars will spend most of their lives fusing hydrogen to helium in the core. That would say main sequence star, 主序星带. What they are doing is fusing hydrogen to helium, and their fate, 命运, the fate of demise is death, depends on their mass. Okay, let's look at this. So we will first talk about the small stars. I should reorganize the... Okay, let's look at the small stars. Okay, so for small stars, it is believed that it's very likely that there's no layered structure, 没有分层. It's fully convective. And for very small stars, which is based on the HR diagram, they are here. And it's red here. So it's also called brown dwarfs or red dwarfs. And the low mass stars are likely to be fully convected. Therefore, there's no shell burning. I will tell you what is shell burning later. And there's no red giant stages. So these kind of stars spend their whole life burning hydrogen. The procedure can take very long. Therefore, there is an interesting observation. That is, smaller stars live longer. Okay? And at the end, they will turn quietly into white dwarfs. So this is the fate of a small star. It's very simple. And now we go to the fate of a sun-like star. Stars like our sun. Its fate is actually like this. Okay, so what's going on? When it's at the main sequence, what it's doing is the so-called hydrogen burning in the core. That is, hydrogen atom collapse to the center of the star and fuse into helium. Okay, that would be so-called core burning. That is, the nuclear fusion reaction takes place in the core of the star. Okay, and then later, at some point, it will turn into a subgiant and then a giant. What's the difference? Why does it turn into a giant when it's older? Okay, this is because at this point, there's already a core of stable helium. And I think I have some more text description here. Okay, giants. Why there's giants? Giants are the products of shell burning. So in the main sequence, all we have is core burning. But for the giants, we have shell burning. So this is the explanation. Usually at the beginning, fusion of hydrogen to helium initially takes place only in the core. And once the star exhausts the hydrogen field in the core, the nuclear reaction no longer continues. And the core, which is now made of inert helium, begins to collapse because of gravity. And then the collapse brings hydrogen inwards. The hydrogen was originally at the outer parts of the star, which is now brought inwards to form a shell around the core where the fusion of hydrogen resumes. Resumes means restart. But now, the difference between the core burning and shell burning is the ignition zone is now closer to the star's surface. Therefore, the luminosity of the star will increase. And this kind of near-surface heating also causes the outer layer to expand, resulting in a larger surface area and a lower surface temperature. So this is a kind of interesting combination. It's higher luminosity, but lower surface temperature and larger size. That's the formation of giants. So come back to this figure. At the subgiants, stage, we have an inert helium core and a hydrogen burning shell. And then when it enters the almost like a between subgiant and red giants, we now have the star will with a helium burning core. Now the helium will also start to burn, and a hydrogen burning shell. And at the red giants, it will have an inert carbon core, hydrogen burning shell, and a helium burning shell and hydrogen burning shell. So basically, different giant stage represents different onion structure. So that's shell burning. And that's a relative size of today's sun and the red giants. Then, at some point, the sun will turn into a planetary nebula, 行星状星云. Okay. And it's a product of star expansion and material ejection. So what's that? What does that mean? So, fusion of helium, mostly to carbon. So the red giant stage with the carbon core, at the late stage of red giant, the reaction rate is extremely sensitive to temperature. How sensitive is proportional to the T to the 40th. So you can imagine a small fluctuation with temperature will result in a size change like this, because it's so sensitive to temperature. This means a small variation in temperature causes large expansion or contraction of the star's outer material, and this leads to pulsation, 就是脉动它就是看起来像这样子。Builds up and finally is large enough to throw off the atmospheric material, because its pulsation is so intense that it starts to throw away its material. So, at the end, the deeper layer of the star are exposed, and the hot layer emits ultraviolet photons to ionize the ejected material that surround the star. So, which means this is a planetary nebula, 猫眼星云. This actually all come from the same star, and the star itself throw away its clothes. 开始脱衣服了 So, and these are the clothes, and the star shine his clothes with its UV light. So these are the ionized material from the star. That's at the final stage of the red giants. And once the star throws away all of its clothes, its atmosphere, it will enter the white dwarf stage. Okay. Then it's the CO, carbon oxygen core of a star. After it throws away most of its outer material. So the star is now naked, 就是没穿衣服了. Okay. And the material no longer undergoes nuclear fusion, and gravity will make the remnants denser. Remnant 就是残余的东西 denser. So for stellar remnants with less than 1.4 solar mass, which is so-called Chandrasekhar limits. It's a physical term. Infinite gravitational collapse can be resisted by electron degeneracy pressure. Okay, what does that mean? Electron degeneracy pressure in Chinese 就是电子检定压力. In short, electron likes to stay in the orbit. It doesn't want to move closer to the nucleus. That would be the electron degeneracy pressure. And if you want to force the electron to enter the nucleus, you need to give enough external force. And here it says, for a small star like our sun, at after the nuclear fusion stops, the material will start to collapse. But because the mass is not large enough, the gravity is not large enough. Therefore, this collapse will not result in electron entering the nucleus. 就是你的力量没有大到可以把这个物质里面的电子压进它的原子核。In other words, the material will be like what you know, like this cup or your body, where all the electrons are in their orbits. Normal material, okay. And white dwarf will gradually cool down and become black dwarf, or turn into a type 1 supernova if it accretes mass from a binary companion. That's something we will not talk about in this lecture. So that's for the star, for the sun. So let me go back here again. Here is burning hydrogen to helium in the core. And once this stage is passed, it will enter the stage of shell burning. These are different kinds of shell burning. And in all shell burning, the star will expand. And at some point, this will lead to ejection of its atmosphere. Then the sun will become naked into a planetary nebula. And then this dust will gradually flow away to the dark universe, leaving a naked star here, and the naked star will gradually cool down. But the star will not become a neutron star, 中子星. A neutron star means the electron is already merged with the nucleus. That will be a neutron star. But here it's not a neutron star. It's just a normal star. And then we call it a dwarf, white dwarf. The end. Okay. So that's the fate of our sun. And next week I will talk about bigger stars. What happened to them? Now I can say, yes. Time for summaries. A group, actually that was already mentioned in Ethan's talk. Please explain bigger this. That would be first. This one actually talks about the R process. R means rapid. 快过程. R process. Please explain this. Here you see there are several notations here. And this one talks about S process. S means slow, 慢过程. Please tell us when this happens. And also this one. Explain this one. And key points. What's our process? Where does our process take place? Where? S process, where does it take place? Where to find the respective nuclides on the chart of nuclides? This means where to find the nuclides on the chart of nuclides produced by R process and S process. Where are they? B group, explain this two graph. The first graph, relative abundance of individual nuclides in the universe. Okay, you see some pattern? And wow, this looks extremely similar to previous one, but it's relative abundance of the elements in our sun. That's in the sun. Key points. What's alpha particles? Why do we have an iron peak? What is nuclear cooking? What is neutron capture? How are the following elements in the sun generated? First, beryllium. Second, oxygen. Third, thorium. Why does the sun have elements other than hydrogen and helium? Many people say there are only hydrogen and helium in the sun. However, you see, this is not true. There are many other elements. Why? Alright, see you next week.